Thanks for the introduction. So today I'm going to tell you about our work on OCO, and OCO enables runtime extension of Open vSwitch with stateful filters. So the context of this work is that of virtualization platforms. So in virtualization platforms, at each of your end hosts, you might have a number of network services implemented for your clients. So for example, you might have stateful firewalls, load balancers, security functions, and congestion monitoring functions. In addition to the software switch. So the software switch is in an ideal position in order to implement these network services because it's already on the path of all packets to the VMs and between the VMs. So ideally, we would like to be able to implement these services directly at the switch on the path of packets. But the issue is that current software switches are unable to express these diverse functions. So in addition to this, we would like to be able to load new functions at runtime on the software switch. So for example, if we have a network event such as a network attack, we would like to be able to load a new program in the software switch to mitigate the attack. Or another example could be if we have a slow connection in our network, we would like to be able to investigate, troubleshoot the issue with a program by loading a program in the software switch, gathering the information, and then removing that program. Okay, so there's a lot of work on extending software switches in the recent few years. Most of this work focuses on implementing these extensions as separate processes next to the software switch. So in these works, they actually implement these extensions in a separate process where they can actually implement pretty much whatever they want to have as extensions. And they have a strong isolation between the process with the extensions and the rest of the software switch. But more recently, 2 years ago at ATC, Jackson and et al. Showed that by implementing the extensions as part of the software switch pipeline, we can have greater performance. So they measured the difference between their implementation of an extension of Open vSwitch with programs running as part of the pipeline and extensions running inside virtual machines with a shared memory between the software switch and the virtual machine. And they measured a 2 to 4 times improvement of performance between the run to completion where the program is part of the pipeline and the VM running in a separate process. So we tried to learn from this lesson, and we actually implemented an extension of Open vSwitch where we run programs or extensions as part of the switch pipeline. So in particular, our programs are in the OpenFlow pipeline. And what we did, as we can see in this example, is we keep the OpenFlow pipeline of Open vSwitch, and when a packet comes in, we will match on the usual fields that we usually have, so such as the destination IP address, for instance. And then when the packet matches these fields, we will go to the stateful filter field, which is a match field in the sense that it will tell us whether or not the program matches the packet. So for instance, here in the first rule, if it matches the first rule, we will execute the anti-DDoS program, and it will tell us whether or not it matches the packet. If it matches, we will execute the action. If it doesn't match, we will continue the lookup in the table. And what's particularly important about these programs is that they can have a persistent state from one packet to the next, so they can gather information and take a decision not on every single packet, but like on a connection or something like this. So there are a few challenges that we needed to address in order to have this extension at runtime and for Open vSwitch. So the first one is probably easier to address because of some previous work on operating systems. So the first one is if we want to be able to extend the switch at runtime, we need to have a way to be sure that our extensions are not going to crash the switch if they have a problem. So if there is like a programming error in our extensions, we want to be sure that they won't crash the software switch. This is particularly important to take care of because we are running as part of the process that is already running the rest of the pipeline. So we don't have like a process isolation between our extensions and the rest of the pipeline. The second issue is in Open vSwitch, there is a key characteristic, in our opinion, of Open vSwitch is its flow caching mechanism. So we need to have a way to extend this mechanism because of our extensions, they are actually, we have to find a way to extend them because of our extensions, and I will discuss this later. So the first one, as I said, is easier to address because of some previous work. So in '92, several researchers invented BPF, so for Berkeley Packet Filter. And today, Berkeley Packet Filter, BPF, is used in the Linux kernel to extend the Linux kernel at runtime with new functionality in a sense. So you can load programs as part of the kernel in different hook points to extend the functionalities. So it's implemented as a pseudocode virtual machine. So it's an interpreter and a G compiler to interpret programs that you load in the kernel. And you can have state persistent from one execution to the next. This state is stored outside the virtual machine in data structures. And you can access this state to a set of external functions. So update, lookups, and delete operations are implemented as external functions on the state. But what's most interesting about BPF is the fact that programs are actually verified before they're executed in the Linux kernel. So there are a set of verifications both before the execution and during the execution of programs. And it checks for, it makes sure that programs will terminate. So it checks for the absence of packages in the control flow graph. So if you don't have packages, you won't have loops in your program, and you are sure that it will terminate. It also checks for memory accesses, so the bounds of your memory accesses, and null dereferences, for instance, and a number of other things. And then there are a few verifications at runtime, such as ensuring that you don't have divisions by 0 in your program extra. In the latest versions of BPF in the Linux kernel, you don't have any more verifications at runtime, so you can actually verify everything beforehand because you don't have loops, so you can actually do it beforehand. So in our work, we actually re-implemented BPF, as I'll mention later. But we kept most of the design of BPF, and in particular of the verifier. We only added one more constraint on programs. So we made sure before executing them that they don't write to packets, and that will become that will become useful later on in the second challenge. So the second challenge is that of flow caching and Open vSwitch. And to try to give you an intuition on what the issue is with flow caching when you had extensions to Open vSwitch, I have to tell you a few words about how it works in Open vSwitch. So in software switches in general, you usually have a number of stages implementing a number of packet processing actions on packets. So for example, you could have to terminate tunnels, apply ACLs, or do layer 2 switching. Now, in a virtualization platform, you can have a large number of these stages in your software switch. So you have to find a way to optimize the performance for large pipelines. One way to do that is to have some sort of a cache, so an aggregation of several stages into a simpler implementation, which would be the cache. But in order to have this aggregation of several stages into a single stage that will run for cache packets, for cache rules, you have to have a common abstraction between the different stages in your full pipeline. So in Open vSwitch, this common abstraction between the different stages is actually the open flow table. So because all of these different stages actually have the same abstraction of the open flow table, you can actually aggregate them into a single stage in the cache. So now the issue with this is that if you try to extend arbitrarily the open flow table in the full pipeline, you have to find a new abstraction, a new common abstraction between your different tables. So if you arbitrarily extend it, you won't have the abstraction that you had before won't be valid anymore. So let's look at the concrete example of how it works and what we had to change in order to make it work with our extensions. So if we have if we have two tables, if we have a first packet that comes in and matches the first rule in the first table, we know that it will apply the action output to 5. In this case, we can directly install a rule in the cache saying that we matched on the field the destination IP address, and then the action was output to 5. If we have a second packet that comes in and matches the second rule in the first table, we will this time have to look into the second table. And then in the second table, we will match on the destination port, and we will have the action again. And we can install a rule in the cache saying that we matched on the destination IP address and the destination port, and the action was output to 3. Now the issue is, in our implementation, in our design, we extended the OpenFlow table with new programs that can have a result, so that can match or not match from one packet to the next, that can match or not match because of the state. So it's not deterministic from the point of view of the cache. So for example, here, if you go through the program A and it matches the first time, you will install a rule in the cache. If the second time you go through the program A, it doesn't match anymore, you won't have the same action in the cache. So we had to extend the caching mechanism of vSwitch, and what we did is we encoded the path through the different BPF programs in the full pipeline. So when we go through the first program, we remember that we executed program A, and we remember what was the result of that execution. So 1 if it matches and 0 if it doesn't match. And then we do the same for program B in our full pipeline. Then we can install a rule in the cache saying that we matched program A and program B. And when the second packet comes in matching the same destination IP address and port, if program B this time doesn't match, we will execute program A, it will match. We will execute program B, it won't match. And so we will have to go to do a new full pipeline lookup in the full implementation. And this time we will go through the first table. We will reach the first program A that we already executed in the cache. We will remember that we already executed it. We will remember what was the result from that execution. We'll go to the second table. In the second table, we'll have the same with the second program, program B. We will remember that we already executed it, but this time it didn't match the packet. And so we will have to select the second rule in the second table. So the second rule that matches the packet would be, for instance, the drop rule at the end. And then we can install a rule in our cache saying the new result from the full pipeline lookup. So here you have to notice that it only works because of 2 design constraints that we applied on programs. So the first one is that programs are actually filters in the flow table, so they are matched fields. And because of that, we can actually encode their result as either a 0 or 1 in our what we call the BPF chain. Second thing is that because programs don't write to packet, we are sure that we don't need to do a new lookup after the program was executed. So for instance, if my program A was to write in packets, and say it could write to packet and it was writing to the destination port, for instance, the lookup through the second table wouldn't be valid anymore, and I would have to do a full lookup again. So because of these 2 constraints, we can actually have this straightforward extension of the cache mechanism. Okay, so a few words about evaluations. So first, we implemented our design on vSwitch DPDK, so the high-performance user space data path of vSwitch. We had to re-implement much of the infrastructure for BPF in user space. So we based our work on HuBPF, which is an implementation of the interpreter and the JIT compiler in user space. And we added support for maps, so arrays and hash tables in our case. And then we implemented a verifier with our additional constraints on the writes to packets. The code is open source, it's on GitHub, and the link is available in the paper as well. In addition to this, we implemented a number of example programs for evaluations. So the first example program is the stateful firewall, where we only have to do a simple hash table lookup and then a transition in the TCP state machine. The second program is much more simpler. It's simply POF TCP signatures translated into BPF programs. So POF TCP signatures are a way to identify the software that sent the TCP packets. So it can be used, for instance, to filter TCP SYN fluids in networks. And the last program, the last example we implemented in BPF is actually a paper from last year at SOSA. So it's a TCP performance analysis program, and for each packet we have to do a lookup to retrieve information on the flow and then add new information, new statistics about the TCP flow. So in the first evaluation, we first compared between Open vSwitch without any of our modifications and our modifications to Open vSwitch without a BPF program. So we want to look at the overhead that we are adding by modifying the caching mechanisms. So what we can see here is that for the case where the first level of cache is disabled, we have a slight overhead between the first two bars. So this will happen when you have very rapidly changing flows, so very short flows in your network. You might have the same effect as if the first cache was disabled, for instance. One thing we looked at is what was the overhead when we had one empty program loaded in OCO. So when we have one empty program, that's the last bar in each of the three cases, we have a slight overhead of about 4 to 5% in addition. So that's the overhead because of the jump to the program and then the jump back to the pipeline in OCO. So because of this last evaluation, we wanted to check to verify the overhead for long pipelines where we have several programs one after the other in our cache. So that will happen if in the full pipeline we have a number of programs that we are going through each one after the other. So what we can notice here is that if we have a large number of these programs one after the other, so for instance for 10 of them, the performance is almost halved. However, we only expect this to happen in rare cases because in each one of these programs you can actually do a lot more than in a stateless flow table. So we don't expect to have a lot of them one after the other to implement whatever you'd like to implement. In addition, this is to compare to the last evaluation. And the last evaluation is an end-to-end evaluation of performance and a comparison to other ways to extend software switches. So here in the paper, we compare between both a VM with both a VM and a separate process. And here I'm only going to explain the separate process case because it's more comparable in terms of isolation. So for the separate process, we have a DPDK application running with a shared memory with a software switch. So both the software switch and the DPDK process are running on their own core on the host. So for each of the three use cases, we measure the performance. And so the separate process would be in orange and OCO in purple. So we can see that we have almost twice the performance with OCO compared to a separate process in this setup. So in conclusion, I'd like to leave you with a few takeaways. So the first thing is we think our work shows that it's possible to extend Open vSwitch without sacrificing isolation and while preserving the caching mechanisms of Open vSwitch. Second thing is, compared to previous work, we think that programs as match fields are actually a way to transparently cache them into Open vSwitch because we don't have to have information from developers about which programs are safe to cache and which are not. And finally, the last point is more of a comment on our future work. So we think that BPF is actually a way to extend other notoriously difficult to extend software than the Linux kernel only. Thank you for listening, and I'll be happy to take questions.
Great work. So is the cache size growing exponentially a concern for you?
So, I mean, it would be the same with, what do you mean by growing exponentially?
I'm not sure if I understand. Can you go back to the... Yeah, so basically you have, if I understand correctly, more cache entries in this case. Sure. And I think it grows exponentially, determined on the number of programs, and because you have 1, 1, 1, 0, and 0, 1.
Yeah, so I'm not sure it will be exponential as it grows, but we don't expect it to be very large because, as I said, we don't expect to have a large number of programs in the same chain. And in addition to this, even if you have a large number of programs in the same chain, you probably are always going to go through the same path in this chain of programs. So you can see this as some kind of a tree, for instance, where depending on the output of each of the programs, you are going to take one path or another. And we expect that one of the paths is going to be more common than the other And so the cache is going to play as usual here.
Okay.
Not sure, yeah.
Any other questions?
Maybe a quick comment. So when Sujata presented, she mentioned the problem of predictability of the performance, right? So I was wondering, so now, if I understood correctly, depending on the complexity of the program that you run, so you mentioned depending on the number of programs, but also of the complexity, number of paths you have, right? You can see different throughput. So do you think this the operators would? I mean, how would you go about maybe like I don't know, being able to reason, given the program, what would be the resulting performance of the entire pipeline that you will build? So I don't know if you see like a way to do like performance-based analysis upfront to actually like give maybe guarantees or like or maybe it's further work, I guess. But
yeah. So we try to look a bit at that, and the issue is you can do pretty much anything in your program. So you could have a number of lookups in data structures, a number of modifications of reading to packets, a number of ALU operations, etc. So it's very difficult to have an idea of what the performance will be. In addition, it's in software, so you have all the issues with the CPUs, with the caches, etc. So it's as hard, I would say, to predict the performance as with any other type of packet processing and software.
Hi. What's the difference between using this with OVS contract? I mean, so if
for the stateful firewall, you mean?
Yeah.
Yeah. So you can already do the same with Open vSwitch. That's a good point. So the difference I say is that in our case, we can actually change the firewall to do only what we want to do, for instance, and we can then reload them at runtime. So for instance, if we don't want to track sequence numbers, we don't have to implement them, and we can just have the rest of the stateful firewall. If we want to do something more than the stateful firewall, we could change it and then load it at runtime. It's an extensibility mechanism, so I mean, but it's just an example in our evaluations, of course.
Great. That's all the time we have for questions. Let's thank the speaker once again. Thank you.